Thank you, everyone. As you know, my name is Kanishka. I'm VP of Engineering at ROKT for Machine Learning and Data. And it's truly a pleasure to be here at the DataEng conference. And it's been amazing talks, and I've really enjoyed it. Hopefully you have too. So today, what I'll do is I'll explore, go through, as my talk says, unleashing the power of real-time machine learning. I'll take you through some of the challenges that you face when you build a real-time machine learning system at web scale. And then we'll go through some of our journey at ROKT. How do we evolve our architecture, and how do we build a system that allows us to meet those constraints when you are at web scale and you need to build something that is real-time. A little bit about me. I'm VP of Engineering at ROKT. I have a bachelor's in mechatronics, so nothing to do with machine learning. I did a little bit of machine learning there, but then later on I got my master in data science, specializing in LLMs. Before LLMs was something, people didn't know what LLMs were at that time, but I'm glad that it's a well-known thing now. I've got about 14 years of experience in software engineering, data, distributed systems, and now machine learning. That's a little bit about me. Skip the rest of it. So before, I'll just give you some context what ROKT does, and then we'll jump into our use cases. Oops. I was looking at the next slide. I thought that was up. So our agenda here, first of all, I'll go through introduction to ROKT, challenges, then the journey that we've gone through. We'll talk a little bit more about the ML pipeline, zoom into it a little bit, and then I'll talk about some of the next steps we're taking in our journey. What is next for us? So here's a little bit about ROKT. We are a global e-commerce technology company, and we play an intermediary role between multiple e-commerce businesses. And what we do is we try to connect them with our machine learning and data so that they can mutually benefit from each other. For example, we could be showing upsells from one business on another business's review page. And it's a complex ecosystem. As you can imagine, during a checkout process, you have the review page, you have the payment page, you have the confirmation page, and you need to have multiple vendors coming together to play in harmony so you can actually deliver value to the end customer. And a lot of the common frustrations that customers might have is an e-commerce business might actually hard-code these experiences. You might always see the same payment options or the list of payment options. You might always see the same list of upsells. And what ROKT does is tries to use machine learning and data, try to solve the paradox of choice, to cut down to the 3 or 2 or the one optimal experience that makes sense for you. And it's optimized and personalized for that individual user. A little bit more about ROKT. So to give you some idea of the scale and what we do, so we work with some big brands. Some of them are not here. For example, Uber, which doubled the number of transactions when we added them. We've got Uber Rides, Uber Eats, some of these businesses that I've listed here. We process about over 1 billion transactions, and we operate across multiple global markets. And so what is the challenge when you're building a real-time system at this scale? So let's just, before we go into that, we just define a few things here. So the two main use cases when you build an ML system is you either build a batch processing system at high level, or you build a real-time system. And the batch processing system, you have some offline process that runs and takes the data, does some data processing, and then runs a model depending on your requirements. Could be daily, weekly, monthly. Then you produce those output, and that output could be used by someone to take action, or might be used to just print some beautiful PDFs or visualizations. It may not actually be action at all. With a real-time system, you have to build a model. You have to actually get the data that is coming into your system. You have to build that model at some frequency, depending on your requirements. Could be hourly, could be daily, but you want it to be much more faster. And then you are making inferences from that model in real time as requests come in. And so as you can imagine, ROKT's requirements are in the real time, based on the title of my talk. So to give you some idea of the scale that we are facing at ROKT, so ROKT focuses obviously on the real-time part. We leverage contextual data such as where you are in the transaction, that this gets passed to us in real time, about what business you're on, what did you just purchase, how much did you pay for it, what product did you buy, some demographic information about the user, is this the gender, the age group, things like that, that's passed to us. And then we also capture historical information about the user's behavior. And that all goes into the ML model, and then the ML model will, these figures are a little bit old, but we'll produce an inference, a prediction, and we'll rank all the offers that needs to be shown to the user in real time. We have about 450 milliseconds latency. That's our P99 latency, and we process about 17 million requests per day. We have a whole bunch of about 60 different models running at the same time, I think maybe more now, and a whole bunch of features that goes into it, and we process terabytes of data. So this is what kind of makes it complex for us, because even if you take a basic logistic regression problem, when you scale it to this, it becomes a lot more complex. And you might have seen this or something similar. People might have spoken about this in various talks. But when you do that, then modeling, which is what a lot of data scientists focus on, becomes a very small part of the big problem. Majority of this problem, then you have a lot of engineering-based problems. You have to have, that's where MLOps comes in. You have to have a lot of data engineering, all of those other problems. So what are those design considerations that you need to think about? So we talked about latency, model drift, data inconsistency issues that you might get. You might get model synchronization issues, data pipeline complexity, testing and validation, monitoring and alerting, security and compliance, cost optimization, and you need to think about your deployment strategy. How do you roll back? How do you deploy things? So this becomes a long list that is completely outside of a data scientist's, purview, and you need to focus a lot on engineering side. So let's go through each of them one by one. So the very first consideration is architectural design. So the system architecture, you need to think about it. And this is overlooked by many professionals in at least in the ML engineering space. And whether you're constructing a real-time system or a batch processing system, you do need to look at and this becomes a primary concern for you. In the real-time system, you need to think about fault tolerance, scalability, and consider options like, should this be running as a serverless? Should this be running on containers? How do you scale this horizontally? And you need to think about designing architecture so that's decoupled. And there are lots of benefits to it. Your teams can actually do test and deploy and A/B testing independent of other systems. And I'll go into detail later. And the second key consideration is data ingestion. And I'm sure you've heard a lot about data ingestion throughout various talks, because this is all about data engineering. The complexity in real-time data ingestion comes in when you think about it. In our case, we are integrated with so many different e-commerce businesses, and each of those might have different definitions for, let's say, product categories. They might have different formats for time. Someone might pass you 1, 0s in a numeric form for male and female and gender, things like that, and age. And date time could be different. So you need to have something that standardizes and normalizes this data, but you need to do this in real time. You can do it in batch, but you have to do this in real time so you can actually make that inference. So you need to think about these, and the speed becomes crucial. It's not working. Oh, I'm stuck on this slide. Can you change it to the next slide? Cool, model training and serving. So you need to think about your model training and serving. You can't be running a model of a Jupyter Notebook, unfortunately, anymore. You can't deploy that Jupyter Notebook, your favorite Jupyter Notebook, in production because it's just not going to cut it. You need to think about that, what we discussed, fault tolerance, scalability, that's not going to work. So you need to start thinking about what frameworks you should be using. Should you be using PyTorch, or TensorFlow, TensorFlow Extended, Kubeflow, Metaflow? There's lots of them in the market. And how do you make sure that you have a process for continuously training and deploying your models so that they are fully automated and you can capture problems that occur and you can actually fix them? Cool, works now. And then real-time inference. So you've decoupled your model training from your real-time inference. You need to have your real-time inference deployed. Think about your real-time inference part has to support low latency. So you have to make those optimizations, make sure you choose the right technologies because speed matters in this case. And then you can think about caching, etc., depending on what your needs are. And ensure that clear and consistent versioning of your models is maintained. And then the other part is data storage. So think about what data storage you need. It depends on your use case. You might need a NoSQL database, you might need a vector database, depending on. If you're working with embeddings, there's a bunch of talks about LLMs and operational side of LLMs. And if you've got an embedding layer and you wanted to pull that, you could actually store that information in a vector database, so you don't have to run through. For example, if you are running, say, a graph, you could actually convert that graph into in a vector space and store it in a vector database. Then you can run a nearest neighbor algorithm on that to look for similarity. So think about the data side of it, how do you partition the data, how do you shard it, and then you think about the retention policies and archiving as well. Monitoring and metrics. So think about how you're going to monitor it, what metrics make sense. You have to break down your metrics into, what are some of the business metrics, some of the model evaluation metrics, what are some of the model performance metrics, what are some of the more metrics that are monitoring your underlying infrastructure. Think about anomaly detection and what kind of technology will you use to actually track and capture these metrics. And you need to have some sort of a dashboard to monitor it. And you've got, obviously, think about security and compliance. Think about your GDPR regulations and make sure that you're compliant with various regulations which apply to you. And then finally, think about A/B testing. That was about how do you roll things out. So you want to be able to know when your new model, because you're going to continuously be improving your model. So you have to know when your new model is better than the old model. So once you define your metrics, then you need to have some way to roll out the new model and then measure the difference and then be able to scientifically say that, okay, this one is now this is better than the old one, then you can increase the traffic to the new one. All right, so that was some of the very high-level concepts that I discussed. So how do we apply this in ROKT, and what was our journey? Cool, so I've broken it down to just highlight 2 phases. We went through lots of different iterations, and like I said, I've been working at ROKT for 6 years, so we went through lots of different iterations and broke our model down into small microservices, and we got it wrong, and we went and learned from our mistakes. But this is the very simple architecture, a bunch of things I haven't discussed and I haven't put there because they're trade secrets, but this is the super high-level one. Do you recognize this, Claudio? Claudio used to work at ROKT, and he actually interviewed me when he was kind of leaving, and I got the job at ROKT. So this is very familiar to you. You will recognize. So what we do, let's just go through the high-level request path here. So external API is when a user goes through the checkout process that uses, like I said, the contextual information, demographics, and some other information sent to ROKT. This is all in real time. As this comes in, then we could have 100 different offers that we can show to the user. And what we do is we will pull that from the available candidates, and then we go to our data enrichment system. And this data enrichment system is decoupled. And you can double check, you can use this system to normalize, clean your data, and then enrich it. If something is missing, it will add it, and it will enrich it, and it will send it back. So you have the complete information to make that inference. And then it goes to the, enrichment API, it just allows you to decouple it, and you have a bunch of services that could sit behind that, could be running on EC2s. In the early days, we're running a lot of it on serverless, so we're using a lot of Lambdas and EC2s. And that's because we were a very small team, and that made sense to us, and at that scale as well. And then inference is made, and then some auction runs, and the winner is chosen, that's sent back, and then the offer is shown, and the user's interaction with that offer is then logged somewhere in a, say, S3 bucket, and that goes in some data warehouse, and then that process, then the ML models will capture all the historical information, then they will actually train, and then this cycle goes on and on and on. This is how it works. And this is what we did in the early days. Now, the phase 2 of it, as we scaled, we moved away from a lot of the serverless and AWS hosted services, because the economics of it didn't make sense to us anymore. Running Lambdas didn't make sense anymore because it became super expensive. So what do we do? The overall architectural patterns are pretty much the same. There's a whole lot of microservices, and they are decoupled. However, we started to replace where we had Kinesis or we had SNS SQS type of architecture. We replaced those with Kafka. We started to host our own Kafka. And then we run this Kafka. So all of the compute that we run, we decided that we will standardize it, and we use Kubernetes clusters. And then we started running our own Kafka that runs on Kubernetes. Our ML pipelines run on Kubeflow and TensorFlow Extended, and all of those run on containers that run on Kubernetes. We used to just run S3 as a data lake, and people will go and try to pull the data using Athena or pull that data into Redshift. We started to add, we use Iceberg that will allow us, basically, this is a Delta Lake. Databricks has got a product called Delta Lake, and then we started to compare Delta Lake and Iceberg and Hudi. We started to choose Hudi in this case. So we standardized our kind of data lake as well. What else? So in the other part of it, when we started to use TensorFlow Extended actually has an inferencing engine itself. So it's called TensorFlow Serving. We started to actually use TensorFlow Serving as well. And then one of the things that I mentioned was data skew and data drift, data consistency. When you are running a real-time system, the context that you get about that request to make an inference on that, for example, you need to give it all the features to give you back some prediction. You need to make sure that the feature definitions that you've trained your model on that's offline is the same as online. So if you don't have that, you'll get data inconsistency, and you'll get skew, and the results, basically the performance of the model gets degraded. So what do? We looked at a few different options. We obviously, feature stores are a solution that is standard to use in industry to solve this problem. We looked at a few different solutions. We decided that none of them fit our requirements, especially the latency requirements. So we started to build our own feature store as well. And that's, I guess, the last bit of it that is different here. And that's how we evolved it. I guess the main lesson here is that we didn't go with a big bang and introduce a lot of different solutions and introduce Kubeflow from day one, even though 6 years ago, Rokt was, about 100 people. And the engineering team was probably 30, 40 people. We still didn't think we should be building everything from scratch ourselves. We started to go step by step. We are about 700 people, 250 engineers now. At this point, we have, and our business metrics, our revenue and profitability, it makes sense to start actually hosting and Kubeflow ourselves. And it's economic. It doesn't make sense for us for our cost per request to be increasing in tandem with our revenue. So we need to start hosting, it makes sense to run Kubeflow ourselves. Some people manage it. It's most cost effective. So don't go from day one and try to, I guess the same theme that was discussed in the panel, don't go for the shiny tools. Just assess it and make sure it makes sense for your business. So I'll zoom into the ML pipeline part. And what are some of the components? So we can break it down to different components. So what are those components? What are the responsibilities of each of those components? So you have the data ingestion component in an ML pipeline. Then you have to do data validation. You have to do some feature engineering, model training, model analysis. Then you got to do model deployment, and then you do model serving. So how do we achieve this? What do we do at ROKT to achieve this? So we run all of this on a stack. This is our stack. We use our ML pipelines run on Kubeflow. This is a product, an open source product from Google. And then the components are TensorFlow extended components, and then the serving is done by TensorFlow serving. And all of this runs on Kubernetes, which allows us to scale horizontally as we need. So it could be running on a bunch of GPU instances, and then you got containers that run and do the model training on top of those GPU instances. So the details of this is how I guess the model training works. So you've got a bunch of components. StatsGen, for example, will generate some basic statistics about your data depending on the features. What if they're continuous or categorical, whatever those features are, then it will, if it's continuous, for example, it will give you what's the mean, what is the average value here, and what is the standard deviation, max mean values for categorical features. Will give you some different statistics to make sure that there's no outliers in your data. It makes sense. And then for A/B testing, and I'm skipping a bunch of slides here. I know it's too late. And then the A/B testing, it allows you to do, so if you've got a champion model, you can deploy 3 or 4 challenges at the same time. You could be monitoring them and looking at your business metrics and model evaluation metrics and online metrics to make sure that in comparing them and making a decision when to promote a challenger or when to kill a challenger. But what are those specific metrics? You can group them into, like I said, model performance metrics. That is, for example, inferencing, latency, response time, its model staleness. How long, when was the last time the model was trained? If it was trained, if you think that you've done some analysis that your model training staleness correlates with some business metric, and the more stale your model gets, the more you lose money, then you need to make sure that there is a cutoff point. And after that, you need to raise an alert and make sure that your model is not too stale, because it will have a massive impact on your business metrics. Some model evaluation metrics, if you're running classification, could be AUC, log loss, etc., and it could be MSE and whatever for regression, depending on your task. And then you can have specific metrics around model drift, looking at distributions of data. You can look at data quality, and then some infra kind of metrics. So what are some of the next steps we're doing? I mentioned feature store. We looked at a few different vendors. We looked at Feast, which is an open source project. We looked at, I don't want to mention the name of the vendor, but we looked at this other vendor that's really popular, and then it didn't really meet our requirements, so we actually had to reluctantly build a feature store ourselves. And I think Evgeny is in that team, so you're building the feature store, and that's going to be, we're currently in the phase where deploying it, and we're using deploying some simple features, and then we're going to deploy some complex features through the feature store. That's the next step for us. Oops. And then what we're doing is, as our teams are growing, we are scaling across 3 different engineering centers now. We've got an office in Seattle. We've got engineers and machine learning engineers in Seattle. We've got an office in New York, a whole bunch of ML engineers there, and we've got a bunch of ML teams in Sydney. So we've centralized. We built an ML ops team, and at some point it becomes, you need to make it easier for the ML engineers to define their pipelines And they don't have to worry about what's the underlying infrastructure, what kind of GPU instance they need to run, how many GPUs it needs to have. All they need to do is, or how frequently, whether they need to incrementally build their model. We are building a framework that it's almost like an serverless ML. So all they need to do is define their pipeline, define how much data they need, how far back the data needs to go, and how many times it needs to be updated and run. So that's something that we are working on. And then the other big problem that we have is that, as you can imagine, there are lots of vendors that we're working with, a lot of brands. We get a lot of data and a lot of different demographic information, a lot of contextual information, but we don't get enough time. We don't have enough people to go and explore and run EDAs on each of the data, so each of the data points, and find correlations with whether this makes sense to be added as a feature. So some way to automate this will be very beneficial for us. So we are working on some way to automate at least feature selection and feature importance ranking, and then there'll be some human in the loop who will decide whether we should actually add these, and when we add it, we'll do some offline analysis, etc. So this is what this is our journey, and that's it from me. Thank you, everyone.